What's going on, class? Welcome to another lecture video. Dr. Nee here, and we're going to continue the concepts that we started in the last video, chapter 12, where we're looking at the slope and deflection of beams. Now, I want you to know that I understand, and admittedly, this concept can be very involved. These problems can be long, and there are a lot of room for errors and small mistakes. But I wanted you to know that I do not think that this is something you can't grasp. I think the concepts are able to be understood. It just takes close attention and patience to make sure you are able to work through it. And so today we got two example problems I'm going to go through. Right here in front of us is 12-7. That's what we're going to do. And again, very similar to the ones we did last video, but we're going to continue to walk through it so we can have more practice in the process. So this says here before us that we have an A36 steel beam. Right, so steel beam. That means we already know the modulus of elasticity, if that is necessary, 29,000 ksi. But it also tells us it has a depth of 10 inches, a constant moment m sub naught. So this isn't a number. We're just going to use m sub naught for a moment, and it causes outer stress, a stress in the outer fibers to become 36 ksi. So here's what it's asking us. It's asking us to determine the radius of curvature, which is rho, and the beam's maximum slope and deflection. That's what we need to find out. So to start things off, let's just start with the radius of curvature equation that we understand and we know, and that is as so. The moment is m sub naught, and this is over EI, right? And so in order to solve for the radius of curvature, let's go ahead and isolate rho, and that is going to be now written as EI over m sub naught. Now we don't know what m sub naught is, but we're going to go ahead and believe it as such. But we do know that there's a relationship between the stress, right, and the moment, MC over I. So what we can do in this case is we can rewrite this equation in terms of m sub naught, and then we can plug it into our radius of curvature equation in order to solve for it. So here's what we have. M sub naught is equal to the stress. It's going to be sub y times I over C. So now let's plug this into that equation there. And here's what we should have. Rho is equal to E. There's an I up here. Down here, we're going to have this, but the C is going to come up here. And this is going to be I. Now, these I's cancel out right here. And now we can put in the value for E, the one that is good to memorize when it's still 29,000 ksi. What is C? Well, the distance from the neutral axis to the exterior. And so this is a depth of 10 inches. So C is going to be 5. And then sigma y, we're told here is 36 ksi. 36. That's in ksi. This is ksi. And that's in inches. What is the value of rho? Well, you do your calculations on your calculator. Let's see what rho is. 29 times 5 divided by 36. Okay. I have here 4,000. It's a pretty big number in terms of inches. Sorry about that. I actually just lost the calculation. There it is. 4,027.77 or 0.78 to round up. That's inches. What is it in feet? 335.6. Or we can just say 336 feet. All right. That is our rho. That is our radius of curvature. That's our radius of curvature right there. That is the first part of this problem that we're asked to solve. Now, the next part gets pretty involved because it's going to mean that we're going to need to then jump into our process of solving for m sub x, right? Which we know to be EI times D2 over dx. That's what we know to be the case. Now, I want you to know really quickly, if you watched the last video, you may have noticed that I continued to write dv over dv, which was a mistake. It actually should be dv over dx, and I wrote it correctly here. So if you watched the last video, sorry if I threw you off with that, but nevertheless, all the concepts are consistent. All of the things are correct and true. I just kept writing the derivative wrong, that's all. But anyway, EI d squared v over dx squared is equal to our moment. It's equal to our moment. So the first thing we need to do is determine what does mx equal to. And if we were to draw our beam and cut it right there in the middle, we know that we have here an m sub naught, but there's no force right here. There's no force happening anywhere along the length of the beam along x. Only thing we would definitely have here is another reaction moment, right? Another reaction moment that's happening right at the fixed end. This moment will be written like that. And that would be m sub naught. Now the reaction moment would be the opposite of what this internal moment would be. So because it's external, it's external. So while the reaction moment internally would have wanted to be, or the internal moment at this face would have wanted to go that way, we're going to write the external reaction moment as going that way, and it's going to be equal to whatever applied moment is causing this internal moment, and that is m sub naught. So we will write, in other words, m sub x, this equation, m in terms of x, as equal to negative m sub naught. That is our equation that we're starting with. All right. So we can just start off by saying, all right, EI d squared dx squared is equal to a negative m sub naught. That's our first equation. That's the moment equation. If you take the derivative of that, we're going to get the slope equation. Excuse me. It's going to take the slope equation as dv dx. That is equal to m sub naught, negative m sub naught, x plus c1. That's our second equation. X plus the constant. What is the next equation? EI v is equal to negative m sub naught x squared over 2 plus c1 x plus c2. I want you to be aware of something when it comes to preparing to solve for these constants after you got your equations. I want you to know that when it comes to our cuts, right, you can actually determine x as going right to left or left to right. You see I have an arrow right here going both directions. So what we're going to do in this case, we're going to say that x starts on the right and it goes to the left, all right? So in other words, you could think of this as the cut. The equation stays the same. This is still the end. But let's look at x going from right to left, all right? So if x is going from right to left, what are some of the boundary conditions that we can establish in our process of solving for C1 and C2? Well, here's one. We can say that when x is equal the full length of L, when x is equal to L, then the deflection is what? It's 0, because that's the fixed end. That's one boundary condition we can say. And I'll just put BC right here for boundary conditions. What is something else we can say? Well, we can say that when x is equal to L, the slope is what at a fixed end? The slope is also 0. We shared that in the last video. These are boundary conditions. We can say that when this x going from right to left is the full length of L. So now we can set our equations equal to these values, equal to 0, more specifically for each case, and we can find out what these constants are or will be. So let's start there. Let's start there. We know that mx again, I'm gonna write this again just so you all can see it. Mx is where we started at, right? You got EI, d squared v over dx squared equals negative MO. Just gonna rewrite these for you really quick. EI dv over dx, this is the slope, is equal to negative MO x plus C1. And then the last one, by the way, this is slope. And then deflection is V equals negative M naught x squared over 2 plus C1 x plus C2. All right. So let's use our boundary conditions. And I'll write this up here again just so we can have it on the same page. At x equals L, V equals 0, and at x equals L, theta, which is the slope, also equals 0. So we can now say, all right, let's start with this one right here. Let's set our theta equal to 0. 0, right, is equal to negative M sub naught. Instead of writing x, we're going to write L because we're talking about when x is equal to L, and we're going to say plus C1. So what does that mean? If we were to solve for C1, C1 is equal to M sub naught L. That's one of our constants. What's another one we can do? We can say 0 is equal to, down here, set that equal to 0, when x is equal to L, M sub naught L squared over 2 plus, now what can we do in this case? We don't necessarily need to write C1. We can go ahead and just write what we know C1 to be, M sub naught L. And instead of writing that x, we're just going to also write another L, which is really L squared plus C2. So now we use that to solve for C2. And we can come down and discover that C2 is equal to, so that's L squared. And let me write it this way. This is going to be L squared. So we got negative M sub naught L squared over 2. Then we got M sub naught L squared, not, as a whole. So that just simply means that C2 is going to be equal to a negative M sub naught L squared over 2. Take a moment, make sure this makes sense algebraically for you. When we solve for C2 using this equation, this is a negative M sub naught L squared. You're going to subtract that from here. So you're going to have a half of a M naught L squared, but then you got to move to the other side. So now you have a negative M naught L squared over 2. So that makes sense algebraically. These are the constants that will go into these equations. All right. Now from there, we're still in the process of having to find the maximum slope and deflections. So let's rewrite our slope equations now with our appropriate constants, right? So the slope equation, that's what we're doing here. Just doing that to let you know that's what we're doing here. This is going to be EI d squared V over dx is equal to negative M sub naught x plus M sub naught L. Cool. That is our slope equation. Our deflection or displacement is how it's worded in the problem statement. Deflection, displacement, all referring to pretty much the same thing. So here in this case, we're going to have EI V is equal to negative m sub naught x squared over 2 plus m sub naught L x minus, because this is a negative, m sub naught L squared over 2. So those are the official equations that include the constants that we use boundary conditions to find. Make sure you soak that in. We got our equations originally. Just to review really quick. By finding out what m sub x is, we took the derivatives of, or the antiderivatives of it, rather, to get these equations. We use these boundary conditions to then solve for what those constants are. And when we solve for those constants, we basically rewrote the equations we cared about, the slope and deflection, including these constants, and this is what they look like. So now we have one more step, because it didn't just ask us to find these equations. That would have been a solid problem in and of itself. But what it's asking us to do is actually find the maximum value of the slope, the maximum slope and the maximum displacement. So I ask you, as you look at this problem right here, if we're considering x going from right to left, where would the maximum displacement take place? At this end, right? Because that's where the moment is being applied. Not only that, that's where the maximum displacement would take place. Because if you were to draw the exaggerated shape as our play-by-play designates, this would look something like this because of that moment. And so now you would have, from its original location, maximum displacement, and then the angle of the tangent line will be the maximum slope. All right. Hope y'all can get these concepts, grasp them. So what that means is, using our same convention of x going from left or going from right to left, the maximum would take place. The max location would be when x is equal to 0, and that goes for both the slope and the displacement. So now what we need to do is simply plug in 0 for x in these equations, because that x equals 0 is where it's located. So now we're just going to go ahead and say, for the slope, the maximum slope is this, right? And at this step, this is where we can't forget that over here we have this EI. So we're going to need to move this EI to the other side when we plug these things in. And if you do that algebraically, here's what you should get, right? The maximum slope is going to be m naught L over EI. Why? Because when you plug in 0 for this x, that term is gone. That term is completely gone. And when you divide both sides by EI, now you're just going to have m naught times L over EI. So this is the maximum slope. We could find the number if they gave us the number for m sub naught, but they didn't. The problem just kind of used m sub naught. So that's what our answer is for the maximum slope. Now the maximum displacement or deflection, or however we want to call it, we plug in 0 here, that term is gone. Plug in 0 here, that term is gone. So now we're dealing with just this term, and we're going to divide EI by both sides. And what that will give us is negative m sub naught L squared over 2 EI. That, my friends, is our maximum displacement. So sorry, man. I did not realize I was shifted down. So I'm gonna let that sit there and let that ride for a little bit. All right. So let me say that again. So when you do, when you find out that the maximum location for both the slope and the deflection, now these could be two different numbers, right? But we know that in this case, both are going to happen at the very end when x is equals to 0. When we plug in 0 into this, it's going to be gone. When we plug in 0 into these x's, it's going to be gone. And this is what happens when we move EI to both sides. And these are our values. I hope that makes a lot of sense for you. Go back and rewind it if you need to. It's a lot of algebra. Once you kind of get your once you get these equations established, a lot of this is just algebra, identifying your correct boundary conditions, and then rewriting your equations the more information you get. So please do what is necessary to get that. We're going to do another one of these example problems right now, right away, to help you be able to see more of how this thing works moving forward. All right. There you are. So here we go. Let's move on to the next one. That one was 12-7. And for this one, we're going to do 12-8. 12-8. Now, this one could be a little bit more involved. Why? Well, take a look at it. It actually has an x1. And then over here it has an x2. So this problem is basically already telling us, it is already telling us that we're going to have to go from both sides in this case. So I told you can go from either side, but going from both sides are going to give us an opportunity to see how both equations can kind of meet at a certain location and be equated to each other in the process of solving their values. So let's start things out by getting, in this case, we would need to get some reactions, really, right? We will need to get some reactions because we're going to have C here, CY. And then we probably will have, because this is coming down, it's going to want to rotate that. It's probably going to be a negative Y here, a negative AY here. That's probably going to be the case right there. Let's just quickly determine what that is by some of the moments about C, because we're going to end up going to cut here. Obviously, we're going to have to do a cut here, and we're going to have to do a cut here based on what they already told us they want. So let's sum the moments about C. If this is positive, some of the moments about C here for the entire thing means that AY times A minus P times B. Any other forces? No. Set that equal to 0. Solving for AY would give us, going downward, AY would be equal to PB over A. PB over A. And that's going downward. If we would have wrote the arrow, if we didn't anticipate and wrote the arrow up, that would have been a negative number. But I'm going to keep that there. And what I'm going to begin now is begin to show you, hopefully both of them at the same time, right? How both of these equations are developed on both sides. Over here, we're going to call this the x1 side. We're going to call this the x2 side. And if we were to draw a cut here for the x1 side, we know that there would be a downward force here because of AY of PB over A. There will be a V here going down, obviously, but we're not worrying about the shear equation. We're going to get the moment equation. We're going to get the moment equation, right? And this is going to be determined by MX. Over here, drawing it cut from this side, boom, boom. We know we got P going down here. We're going to draw a moment here. And there's obviously a shear force going up here. So to start things out, what is the moment equation? If we were to sum the moment about the cut on this side, we sum the moment about the cut this side. Remember, x1 is going this way. It's going to start on that side. So in this case, mx is going to be equal to a negative PBA over A times x. So for our equations, we will write EI d squared v dx squared is equal to negative PB over A times x. What is the antiderivative of that? Well, the antiderivative of that is EI dv dx is equal to negative PB x squared over 2a plus C1. Now to get the deflection equation, we're going to take the antiderivative of that, which is EI V equals negative PB x cubed over 6a plus C1x plus C2. That's this side. That's the x1 side. What is this side? Well, mx is going to be equal to, on this side, because it's creating a moment around the same way, it's going to be negative p. And remember, this is a distance here, x2. So negative p times x2. Negative p times x2. So the first equation, EI d squared over dx squared is equal to negative px2. Next, EI dv over dx equal to negative px2 squared over 2 plus, we already use C1 and we use C2, so let's call this C3. Make sense? All right, and then the displacement equation, it's going to be EI V equal to negative P x2 cubed over 6 plus C3 x2, right? We're calling these x2. We can call all these x1 if you want to keep it distinguishable, right? All these are x1s, all these are x2, plus C4. Now, if you need help with this, please come to office hours. Please shoot an email if anything leads confusion. Definitely want to make sure you understand this. But at this point, it's really all algebra. You did a little bit of statics here to solve for m sub x. That's how you get your first equation. And then you're doing antiderivatives from there. Now we're going to have to solve for these constants. And that's what we're going to do for the remainder of this example problem. And in order to solve for these constants, we're going to need to determine what our boundary conditions are. So staying on this page for now, what are the boundary conditions that we can write? Well, we know that at x1, when x1 equals 0, the displacement v is also equal to 0, right? There's nothing moving right there. Nothing moving right there. We know that when x1 is equal to a, what's happening when x1 is equal to a? Well, and again, I'm gonna put that BC, these are boundary conditions. When x1 is equal to a, because that is another support, we can also say that the displacement is 0. Got me? So let's start here. Let's start here by solving for the C1 and C2, because that's going to help us out quite a bit. So coming back over here on another sheet of paper, make sure we have enough room. We'll rewrite those boundary conditions again. X1 is equal to 0. The displacement is equal to 0. And when x1 is equal to a, the displacement is also equal to 0. So let's set the displacement equation equal to 0 over here. All right. So 0 is equal to, what was that first displacement equation? There it is right there. So 0 is equal to negative PB. X1 is going to be 0 because we're setting it equal to 0. So 0, 6a plus C1 times 0 plus C2. What does this tell us about C2? If this is going to be canceled out with the 0, that's going to be canceled out with a 0. Therefore, C2 is equal to 0. That's the first thing that we know. Now, for this next one, we say that when x1 is equal to a, the displacement is also 0. So let's write this same displacement equation, set it equal to 0. But now instead of plugging in x equals to 0, we're going to say x equal to a, negative pb times a cubed over 6a plus c1 times a. And we already know c2 is equal to 0. So we don't need to write c2. We don't need to write c2. So if we do this and we solve for c1, obviously this is an a, that's going to be a cubed. We can cancel those out. You're going to divide both sides by a. Algebra should tell you that c1 is going to be equal to p a b over 6. So we have two constants solved for the right side of the equation, for the x1 side of the equation. Now, for the next one, and just bring this back into focus, for this side, the question is, what type of boundary conditions can we say for this side? Or what can we say, anything or any conditions that we can say for this side? Well, we can't necessarily say that when x2 is equal to 0, that the displacement is 0. Why? Because there's no support there. That's actually going to be some displacement happening. But we can say this, that when x2 is equal to b, x2 equal to b, sorry, I'm about to put 0. x2 is equal to b, the displacement is equal to 0. All right, these are conditions for this side of the equation. What is something else we could say? Well, if you remember at the beginning of the last lecture, it's not just boundary conditions that we can be concerned with, but there's also conditions where we meet, right? We could say that when the deflection equation, right? The deflection equation for this one, 2, that's what this one is. When x is equal to b, it should be also equal to the same deflection equation of 1 when that x1 is equal to a. What that is saying is that this equation here, when x2 is equal to b, that's at the same location of when this equation has x1 equal to a. So this is how we can write it. V2 when x is equal to b is equal to v1 when x1 is equal to a. Not only can we say that about the deflection, we can also say that about the slope. But here's something I want you all to pay attention to with the slope. All right, theta 1 is equal to a. When it comes to the slope, it is actually equal to the opposite value of that slope. So when theta 2 is equal to b. So theta 1, when x1 is equal to a, is equal to the negative of when theta 2 is equal to b. Keep that in mind when it comes to setting these equivalents with the slope. All right, so these are some conditions that we want to keep in mind as we now prepare to solve for these constants, C3 and C4. So let's do it this way. Matter of fact, I'm gonna slide this up so I can keep an eye on it. All right, drawing a line there. So let's start off with the first one. Let's set these. Let's go with this one right here. We're gonna go with setting the theta equal to that theta. So we got the value of theta here. This value, well, that's equal to a. So we're gonna say negative. This is theta 1, which means that we're using this equation right here. Negative PB. We're gonna plug in a there, squared over 2a plus C1. We already know what C1 is, so we can just write plus PAB over 6 is equal to a negative theta 2. Well, what is the equation for theta 2? Is this one right here. And we're plugging in B for it. So a negative would make this a positive. Y'all can see that. Make sure it's all in the same thing. Yep. This is going to be a positive P. Instead of writing x2, we're going to write B. B squared over 2 plus C3. We don't know what C3 is, so we're just going to say C3. Now we can use these terms to solve for C3. And if we do that, C3 algebraically would come out to be PAB over 3 plus PB squared over 2. Again, I'm going to say this again. I know I said it a bunch of times. We're using this condition here, which says that when the theta equation, the angle of slope on this side sets x1 equal to a, is equal to the negative of the theta equation on this side when x2 is equal to b. And so we came down here and we wrote this equation. We wrote the theta equation on the one side where we plugged in a for x1, and we set it equal to the theta equation on this side and plugged in b for x2. That allowed this to be the only unknown, right? Of course, we're using p and b, and those are numbers, so we're not treating those as variables. But the only unknown here is this C3. We can solve for the C3, and algebraically, this is the value that you should get. So there's the last thing that we need to solve for, and that is C4. We know C3, we know C3. We need to know what C4 is. To solve for C4, we really could use either of these conditions right here. We could set x2 equal to b and set the whole thing equal to 0. Or we could do the same thing with that we just did where we said v2 when x is equal to b is equal to va when x1 is equal to a. And because we've done things like that before, let's do this one. Let's do this one again. We're going to show this equation here. This is v1, and we're going to set that equal to a. So let's say negative, and I'm going to write it down here, negative p b x1 is going to be equal to a cubed over 6a plus, we already know what C1 is. C1, we're going to write C1 here, PAB over 6. And we're going to put another A out here because that's what this X1 is. We also know what C2 is. C2 is 0, so we don't even need to write anything there. So let me just make this into an equal sign, right? Make that into an equal sign. And now we're going to write the V equation from the other side, and we're going to set X2 equal to B, right? This is V1, and then V2 is over here. So we're going to say negative P times B cubed over 6 plus C3. So we know what C3 is. So let me go ahead and write it this way. C3, I'm going to put that in there, P, A, B over 3 plus P, B squared over 2. And the equation said that's times X2, but we've already determined that we're inputting B for X2. That B is going to be distributed across there. And then we have plus C4, plus C4. So we can just write that as plus C4 because that's what we're solving for in this case. All right, put that out of the way. Take a look at that, make sure it makes sense to you. Now I'm going to write what this algebraically should come out to. What it should come out to when you're able to rearrange and restructure everything and solve for C4. And what that should be is this. C4 is equal to negative PB to the third over 3 minus PAB squared over 3. That's if you were solving for C4. All right. Hope you all following along. So far, so good. So now it's a good time to remind ourselves what the problem is even asking us to do. And just to go back to it, it says determine the equations of the elastic curve. So we got the equations, right? We got the equations written here, but we don't have it with the C1, C2, and C3 and C4 entered into these equations. So what we're simply gonna have to do is write the equations for the elastic curve. And for the elastic curves, they're just talking about these equations right here, right? The deflection ones at the very end. We're just gonna have to rewrite these where we use these constants. Sorry, we use these constants that we just determined in place of their C1 and C3 and C4 and accordingly. And here's what you should get, right? For the first one, and we're also going to divide it by EI too, so let's not forget that. Here's what you should get algebraically, P over B, 6A EI times x1 cubed minus A x1 squared. And then the other one, when you simplify it, will give you a negative P over 6 EI. Right, we're moving the EIs from the other side in order to answer these problems. Times negative x2, 3 plus B times 2A plus 3B x2 minus 2B squared A plus B. This one is from the left side, right, where we dealt with x1. And this one is from the right side, where we dealt with x2. These are our official answers in simplified form. Now, I want you all to know something. I want you to know something in case this is alarming you. When you see this on the exam, I understand that there will be ways that you may choose to simplify this that may not look exactly like they're simplified here. But what is most important is you are able to determine what these C values are, and that you do know that these then C values are to be inserted back into these original equations, depending on which one they're asking for. If they're asking for the slope equations, you're going to do these. If they're asking for the elastic curve or the deflection or the displacement, you're doing these, right? So make sure you know where you're inserting these constant values in. But I just wanted to go ahead and write that for you. This is how they should all look if you were able to simplify them as efficiently as possible. All right. So that concludes this lecture. I told you these were some very long problems. Go ahead, rewind, freeze, make sure you're able to follow along as clear as possible so that this makes more and more sense to you moving forward. All right, I will see you all in the next class. Peace.